let's look at conservation of angular momentum. Conservation of angular momentum is the total angular momentum in a closed system remains constant. Let's break this definition down. Let's first look at angular momentum. Angular momentum is rotation and revolution of object or objects around a rotation and revolution axis respectively. So here we have an example of a moon, for example, orbiting around another object that we don't see. And that unseen object's located at the center where r is equal to 0. R is radius. The moon has a moment of inertia I, and this moon is rotating around its rotation axis at a speed of omega. Therefore, it has a spin angular momentum, which is equal to its moment of inertia multiplied by its angular speed. In addition to this object having angular momentum, that's the spin type, it also has angular momentum of the orbital type. This moon is orbiting around another object. It's located a distance r away from this other object. Therefore, its orbital angular momentum is the multiplication of this distance r multiplied by its linear momentum p, where linear momentum p is the mass of this moon multiplied by its velocity or its speed in the direction of p. So the total angular momentum is the sum of the rotational or spin angular momentum and the orbital angular momentum. So in this sketch on the right, they have transferred the vector axis of the spin angular momentum to that of the origin to show you the amount of spin angular momentum compared to the amount of orbital angular momentum, and that the total is the sum of the both. And that black line there is the direction of the total angular momentum. So far, we have the conservation of angular momentum is the total angular momentum in a closed system. Let's look at a closed system definition now. A closed system does not involve transfer of matter and energy in or out. In other words, we're looking at the total angular momentum of just this particular system. We're not looking at any energy being transferred in or out. We're not looking at matter being transferred in or out. We're only looking at this particular object, its rotation around its spin axis, and its orbital motion around the orbital axis. So the conservation of angular momentum is the total sum of angular momentum in a closed system remains constant. So let's go focus on this conservation of angular momentum. Here we're going to look at two systems orbiting around a common center of mass. The common center of mass is where the two colors change. We're going to stop the animation at 2 points. Let's stop it here. Now we want to find the total angular momentum here. We have two objects, each of mass m. They're located a distance r away, and they're each moving with a different speed v. So the total angular momentum is going to be the mass of the purple object times the radius of the purple object times the speed of the purple object, and it's going to, we're going to add on to it the mass of the orange object times the radius of the orange object times the speed of the orange object. So we have the angular momentum when the objects are furthest apart. Let's start the animation again, and we're going to stop it right when they're very close to one another. Now the angular momentum that they had when they were furthest apart has to be equal to the angular momentum when they're closest together. When they're close together, we didn't lose any mass. The masses are the same, but the radius is changed and their speeds change. Notice how their speeds pick up as denoted by these long vectors. So when you take a look at the conservation of angular momentum must be conserved in this closed system. So let's draw our closed system in. Our closed system is going to be everything inside this box. So no mass is going to get in or out, no energy is going to get in or out. So we need to account for all of the angular momentum at all the different points in this orbiting around this common center of mass. The common center of mass is denoted by the red X. So when the objects are furthest apart, they have an angular momentum. When the objects are closest together, they have another angular momentum. Both those angular momentums must be exactly the same, or in other words, conserved. The only thing that's changing is the object's distances to the center of mass, and as their distances change, so must their speeds in order for angular momentum to be the same